understand why we need to study this area called computational topology, right? So we have data all around us, right? It is increasingly becoming a world that is driven by data, right? So it's important for us to be able to analyze data, process it, store it efficiently, right? And understand data, right? So there are several areas that have spawned due to this, right? One is data science, and data visualization is a big part of this this topic, right? For today, we are going to look at scientific data, right? So scientific data is data that comes from various science engineering disciplines, where your domain has a spatial context, right? So what do I mean by spatial context? So if you look at, for example, pictures here that are shown here, so these are all visualizations of various kinds of data, right? So on the left, what you will see is, on the top left, you will see a picture of a tumor in the breast. This is coming from near infrared (NIR) microscopy, right? Below that, what you see is an image of a virus called the human adenovirus. This comes from another imaging technique called electron microscopy, right? The next what you see is something maybe more recognizable. It's the human torso, but this comes from another scan called CT scan. This is something that you probably take when you have when you want to see the bone structures a little bit clearer, right? Next, the green image that you see is that of this is not from the medical world. It comes from the study of materials. So this is a foam-like material, and there's a lot of pores in this material, and one wants to study this pore structure, right? So the data here comes from simulations, so computational simulations, which to study the pore structure. On the right, the image that you see comes from a simulation of the entire universe. This is called the cosmic web. So here one wants to understand what is the structure of the universe in the large scale, right? It turns out that it actually behaves like a web, right? Like a spider's web, right? So you can get a sense that the data comes from various disciplines, from actual imaging devices, and from simulations, right? So what is common to all of this is that the data is measured over a 2D or 3D or a higher dimensional spatial domain, right? So the examples you see here are all 2 and 3D, right? There are a few where you can take this this forward, right? So to 4 and 5 dimensions. So we always work with a domain D, which is spatial, right? And we look at data that is sampled over this particular domain, right? So we focus for today. We will focus only on data that takes real values or scalar values, right? So we talk about scalar functions, right? So f, a scalar function defined over D, takes real values, right? So data that is represented using a scalar function is what we call. Now, of course, when we have data, the first task is to understand what patterns are present in the data, right? What are the features, what is important, what is not important. And so this branch of visualization focuses on taking data and converting it into pictures, so that as a human we can understand these patterns. Now, this is an area, this visualization has been an area of research for over 30 years, and there are several techniques that have been developed over these 30 years. So classic techniques are something called level sets. So this is something we may have seen even in our school, right? So if you have terrains, then one way to display this terrain, the terrain is also a scalar data, right? It's elevation at every point on the plane, right? One way to visualize this is by drawing a collection of curves. Each curve is the set of all points which are at a given elevation, right? So these are called terrain maps, right? This is a classic technique. But when you go to 3D, you can quickly see that this technique does not help you anymore in finding patterns in the data, right. So what you see here is an isosurface, the same idea, but for data taken in 3D, right. So you have now a scalar function defined over a 3-dimensional domain, and you're looking at all points that have a given function value, right. And there are multiple surfaces that you see here, right. And you see that there is no clear pattern. This is actually data that comes from a turbulent flow, right. So these surfaces are very complex, and it's very difficult for us to make sense out of it, right. So hence, classic visualization techniques do not scale very well as the data becomes larger and becomes rich in terms of features, right. But there is still value in these classic techniques, right. So the ISO surfaces or level sets, as they are called, right. An isosurface, I will come to the formal definition soon, right. An isosurface or the level set is the collection of points which have a given function value. So it's the pre-image of a real value, right. So if you take, for example, a CT scan, right, this is over a spatial domain, and you look at all the points which have a given function value, so you can't read it out there. So on the left, what you see is the foot with a value 30. So all points which have function value 30 are connected together, and you get the picture on the left, right. So next you choose 80, and you get something that looks like the skin of the foot, right. A slightly higher value, which is close to 200, gives you the bone structure, right. So you get a sense that isosurfaces are able to help you visualize this structure of the human anatomy, right, which is present inside the data, right. So isosurfaces do have value. You can also extend this to see inside the volume, right. So the surfaces need not be opaque. You can render them as transparent and use that to see inside the domain, like what you see here. You can see the bone together with the blood vessel structure and the skin structure, right. So this is also possible. There are other techniques. This technique is called volume rendering, right. So I'm not going to talk about this. This is all just to motivate why we need to develop techniques to understand data. So data quickly gets very complex. So for example, in the large scale structure of the universe, you have, like I said, this web-like structure, right. So the web-like structure has clusters which actually are where our galaxies lie, right. And these clusters are connected by thread-like filaments, which also house a few galaxies, but they are actually high density regions inside the universe. Now everything else is called the dark web, right. So this is considered the place where there is no matter, right, and that is actually a subject of study, right, by cosmologists. Now quickly this becomes very complex, so you can't make sense when you just visualize the data. So you need some techniques to process this data and visualize things better, right. So one idea is to use features that can be computed explicitly and use them to highlight what is interesting in the data. So let's look at the human torso, for example. On the left, what you see here is this volume rendering. So you take this scan, right, and you try to see through this entire data by mapping every scalar value to some color and of course some transparency so that you can see through, right. Right now it looks like a mess, but what you see on the right, that graph, is a very abstract representation of this data, right. So we'll talk about that, right. So this is called the Reeb graph. We will define it formally. Now what happens is that individual arcs in this graph correspond to interesting features, right. So what one can do is to select, as is being done here, individual arcs and use that to highlight different organs in your scan, right. So this mapping comes for free once you compute the Reeb graph, right. So you can see, for example, that some of the organs corresponded to the lung earlier, and what is being now selected corresponds to the colon structure, right? There you will soon see that there are other arcs that can be selected that correspond to the bones, to the skin, and so on, right? So depending on what kind of a surgeon one is, they can highlight that particular part of the body, right, while still seeing everything in context, right? So this is one application of such a structure. So the idea is to do your visualization in a manner that is sensitive to features in the data, right? So you have interesting features, you highlight them in your visualization, right? So now what you see now is kind of a composite view where you see the individual organs together with the context, that is the skin, right? So this is what I would like to call as feature directed visualization of your data. So there is a user interface. What you are seeing is just a recording of a software that was developed to explore this data, right? So you can see this video later if you are interested. It's available also on YouTube, right? So what you saw on the right, that graph, right, is the topic of today's lectures, right? So let's understand a little bit about topology as well, right? You may have heard the term topology. Topology refers to connectivity, how things are connected, right? You may have heard, if you are a computer science student, you may have heard this in the context of networks. If you are a math student, you have heard this in a more formal sense, right? So to introduce topology, so topology is essentially the study of how spaces are connected, right? So a classic way to introduce this is to say that a topologist is someone who cannot distinguish between these two structures, the coffee cup and the donut, right? Because one can be deformed into the other without breaking or without gluing, right? So that is essentially what a topologist studies, right? What are some characteristics that do not change, right, if you are allowed to deform, right? So clearly geometry goes out of the window, right? So these two structures are clearly not geometrically equivalent, right? Right? So that in that sense, today's lectures are going to be different from your geometry lectures, right? So it is the study of connectivity of space. If you want to think about it more in simpler terms, coffee cup equal to donut. The history of topology dates all the way back to the Euler-Tour problem, right? So this was the first study of topology as an abstraction, right? So you may have heard of this Königsberg's bridge problem, right? So if not, go and look it up. So the solution to this comes from a very nice insight that, so let me state the problem quickly. So you have these bridges in this town, Königsberg, right? And there are islands. So the problem is, how do you design a tour? If you are a tourist, how do you design a tour so that you can walk through all the bridges, but you want to walk through all the bridges exactly once, right, to minimize your energy, right? So question is that possible, right? And can you come back to your starting point? So the trick is not to care about where the bridges are, right, and how long they are, right, but rather care about which islands do they connect, right, or which part of the mainland do they connect, right? So you abstract it out as a graph and then study the problem in the graph. So when you abstract it out as a graph, you are discarding the geometry and storing only the connectivity, right? So you already looked at topology, right? So graphs are a good introduction to topology, but topology doesn't stop there. It's a lot more to topology. So that's the history, but of course, modern topology is the study of various other invariants, right? So we look at a few of them today. One is called the Euler characteristic. This is a number. Then there are more descriptive numbers called Betti numbers, which capture the number of connected components in your space. How many holes or tunnels do you have in your space? If you have empty voids in your space, and so on. Formally, these are represented as groups called homology groups, right? So we will not introduce all the algebra that is needed to do this formally, right? Because that's just not possible today. I'll try to give you a gentle introduction via pictures and via illustrations, right? In a few cases, we will be very formal, right? And introduce the terminology. So that's the plan, right? So this is topology. Now, how does that connect with what we saw till now, right? Till now, we were talking about data and data visualization, and then suddenly we switched to topology. So the connection is in that video that we saw, right? So computational topology is a branch which actually grew out of computational geometry, right? So hence, many computational geometers are also aware of or have been working in this area called computational topology, right, including me. So computational topology is the study of algorithms where you care about the space, how it's connected, how do you store it, how do you represent it, right? How do you compare spaces, right? How do you order them, how do you simplify them, right, and so on. So within this, there is a new area called TDA, right, where you try to use computational topology and the algorithms from computational topology towards data analysis, right. So this TDA has several kind of links, right. So it's a highly interdisciplinary field. There are people from mathematics, topologists naturally, right, who are studying this. There are people from statistics who are studying this, and of course computer scientists, right. So data science, machine learning people are trying to study this, right. But as of now, it is well, I shouldn't say popular. It is studied more by mathematicians and computer scientists because the foundational questions, the algorithmic questions and the mathematical foundations are still being laid. It's a very, very young field, right? Only about 10 to 15 years old, right? So we are not. So it's not even as mature as computational geometry, right? Computational geometry is also young, but computational topology is even younger than that. Okay. Lots of applications. We already saw a few pictures, and so you got a sense of applications. But there's a lot of applications of this area to sensor networks, material science, cosmology, even like day-to-day sports kind of applications are also quite well developed. Any questions? Okay. So. So that was more like an introduction to the entire topic, right? So you get a sense of why we are studying this one structure called the Reeb graph, right? Of course, I cannot cover all the topics that have been studied within TDA, so I've just looked at this one specific structure called Reeb graph, and we will look at it in its entirety, right? So before we start, if you have any questions, I'm happy to answer. We'll also take like a half a minute quick break, so you can relax. Okay, so the question is, what is a homology group? So let me just try to give you a kind of an illustrative example, right? Let's say I have a donut, right? And then I have a sphere, right? So intuitively, we know that these two are different, right? But the question is, how are they different, right? Can you talk about some way to represent this donut and the sphere so that you can computationally say that these two guys are different, right? So a homology group is a group representation of the connectivity of this space, right? So the homology group comes in different dimensions. So the 0th dimensional homology group, right, head 0, captures the simple path connectedness, right, of the space, right. So in the zeroth homology, both are actually equal because both contain a single connected component, right? Both the torus and the sphere are a single connected component. The one-dimensional homology group captures connectedness in a different sense, right? So when you take a path on the sphere, right? If it's a closed path, you can always shrink it to a point, right? While always staying on the space, right? So this is a nice property of the sphere, whereas this property does not hold for the torus. You take a circle and put it on the torus, on the surface of the torus. Depending on how you put that circle, you may be able to shrink it to a point, or you may not be able to put, right? So for example, if you take the torus and if the circle is around the cross section, right, then you will not be able to shrink it, right, into a point.
It has connection with the simple connectedness.
Right. So simple connectivity is one of the characterizations of a sphere versus the torus. The homology group is this graded set of groups that captures connectivity at all dimensions. So 0, 1 through the dimension of the space. Right. So it's a group representation of this connectedness. Okay. So I'll leave it at that. It's instead of going formal. Okay. Any other questions? Okay. So now let's try to look at specific things, right? Like the Reeb graph. So the Reeb graph is a topological structure. That's clear, right? So this is intuitive. It is an abstract representation of those level sets that we saw. Okay, you remember the terrains and the level sets. It captures their connectivity somehow, right? It is that graph that we saw in the video, right? The graph that you saw on the right in the video, right? Why are we studying this structure? We already answered a few. We already gave a few reasons why we study this structure. It supports this feature-directed analysis that you saw from the video. But what we will see in this hour and the next hour is that it's a very simple structure, but it's very powerful, right? It has very nice properties, provable properties, right? It is, as of now, we know we have good algorithms to compute it. So in that sense, it's fast to compute, right? That was not a trivial problem to solve, but we do have fast algorithms to compute it now. Lots of applications that we will see in the last lecture, right? Today. Right. So this is the plan. Given that introduction, this is the plan for the next 2 hours or so, right? We will look at, so now what we will do is before the break, we will look at scalar functions, a little bit more detail and critical points, right? And the underlying theory for introducing Reeb graphs called Morse theory. We will look at that. We will look at level sets and how they are connected, right? We will look at piecewise linear functions, maybe a little bit not too detailed right now. Then we will define the Reeb graph, right, formally, and look at some examples. And after the break, what we will do is we will look at some properties of this graph, right? We will look at special cases when the graph becomes a tree, right? And in that case, it's called a contour tree or a merge tree. There are two ways to simplify this, or two special cases. We will look at a way to reduce the size of the graph so that it's more amenable to analysis, right? So simplification, we will look at that. I will kind of more orally talk a little bit about distance measures, stability, right? So these are some advanced topics which I will not cover. I usually will color code them here, right, in brown. So if you are interested, you can look up the references and learn more, right, about those particular topics and those comments. Right. Finally, we will look at piecewise linear functions in a little bit more detail. And we will look at an algorithm for computing the Reeb graph. And I will close with kind of a list of applications that we have worked on, right, in our group. There are lots of other applications, lots of other groups have also established the use of the Reeb graph. Right. So let's begin with scalar functions. I am assuming that you know all this, but this is kind of a refresher anyway, right? We all know, we all have studied scalar functions from calculus, right? Both univariate and multivariate. So some simple terminology we need to know. So at least for now, for this slide, we will look at scalar functions defined over just R, R2, R3, right? The Euclidean domains. We know what the gradient is, right? So the gradient vector, right? If you don't, or if there is a question, please feel free to interrupt, right? So critical points are exactly where the gradient goes to 0, right? We know this also. So this is the 0 vector. So the points where the gradient vector is 0 vector is exactly the critical points. We will focus on smooth functions. This is exactly where, this is exactly those functions for which not only the gradient is defined, but it is the second derivatives are also defined, right? And we will assume that they are also continuous, right? So these are called smooth functions. So some examples here. So these functions need not, often, so these functions, what we have seen here all have analytic descriptions, but they may not always have analytic descriptions, right? You see some sinusoidal examples here and a cubic example there. Right? What we care about really is not the generic multivariate calculus. We care only about critical points, right, for the purpose of this, this topic. Right? So what are critical points? You may have seen them as singular points, singularities also, right? So what are they? So they are where the gradient is 0, you know how to compute them and all that, right? But let's try to understand them from a more intuitive sense, right? So let's think of this 1D function, right? It's one-dimensional function. How many types of critical points does it have? 2 types, right? So the minima and maxima, right? Right. So these are exactly where the gradient is 0. But let's think about these critical points in a different way. Let's think about this as some kind of a roller coaster, right? And you're at some, so the graph plot of the function, think of that as a roller coaster, right? So and you are at some point, right? And gravity is always acting on you, right? And so you're falling down, right? So at every point, you are either falling down, you're never going up, you're always falling down. Are there points where you don't fall down? If you are a point object, right? Are there points where you will not fall down? These are exactly the places. So what is gravity? The gravity here is just the gradient, right? Because you are bound, I mean, it's a roller coaster ride. You can't just fall directly down, right? So the gradient is along the tangent to this curve, right? So where is the gradient 0? Exactly at the minima and maxima. That's where you don't fall down, right? Okay, so those are the critical points. Now, can we further talk about these critical points as being stable or unstable? As in, I am at this point and I'm not moving anywhere, right? But if somebody displaces me a little bit, right, will I come back to that same point and be stable, or will I roll away, right? So how about the former, right? So what are those points which are unstable, right? So if somebody pushes me a little bit, I just roll away. The maxima, right? So intuitively you know that these are the maxima. The minima are the stable points. So even if somebody perturbs you a little bit, you come back to that point. It's stable, right? There's only one dimension here. So there is, people can push you only in that one direction, right? So the minima are stable in that direction. The maxima are unstable in that direction, okay? But there is somebody who always causes trouble. So that's the point that I show using the brown box, right? Again, brown, it's a little bit advanced, but so these are, these are called inflection points, right? What happens here? No, in terms of the instability. If I push, what happens? If I push you in left to right, you roll away. If I push you right to left, you come back, right? So this is going against the classification we had earlier, right? So just like any other degenerate cases you may have seen so far, we will assume that such degenerate cases do not happen, right? So we'll wish them away. We will later handle them, right, in a uniform manner, okay? So there are only two types of critical points, stable and unstable, right, for 1D. Right? So we have seen this. You actually have, you know how to determine stability also, right? You have done this using the second derivative test. That's exactly what it does. The second derivative test actually tests for stability, right, of the critical point. So the wishing away of the degeneracy, right, is exactly what is captured in Morse theory. So this function f, we call it a Morse function, right? We call it a Morse function if none of its critical points are degenerate, right? As in the critical points are either minima or maxima, right? No inflection points. Does that make sense? Okay. So of course, so this is not, what I have missed here is that f is a smooth function, but we have made that assumption already, right, in the previous slide. It's a smooth function, so the derivatives are defined everywhere, and it's called a Morse function if none of the critical points are degenerate, okay? Right. So now that we have seen the example in 1D, the 2D example will follow straight away, right? Critical points again are exactly where the gradient, now it's a gradient vector, right? So both partials are 0, right? We can again talk about stability, right? You can again talk about a particle or a point on this plot, graph plot of this function, and talk about how stable is it, right? At most points on the terrain, you are flowing down. It's not going to be stable, so we don't care about them. We care about points where the gradient is 0. So those are the blue maxima, the gray minima, and the gray and blue type of criticality. There's a third type of criticality, right? Does anybody know what they are called? Maxima, minima, and they are called saddles, right? If you have not heard the term, they are called saddles, right? And how will you distinguish between the three now? You can again use the gradient test, but you won't be able to distinguish between the three types of criticality. So here you need to look at the Hessian, the second derivatives, right? At least using multivariate calculus, that is what you will do, right? So you will look at the second derivatives. So you will get what matrix? This matrix is called the Hessian matrix, right? And you test for singularity of this matrix, right? If it is non-singular, then you know that you are one of these 3 points, and you further analyze this Hessian, you will be able to distinguish which criticality you are, right? But let's not care about that. We know a way to distinguish the different types of stability, right? Remember that pushing test, right? Can we do that now? If you are at a point, and if I perturb you a little bit, right? And if you come back to that point, right? So if I'm stable, what point am I? Am I the minimum, maximum, or the saddle? The minimum again, right? But the minimum is now like super stable, right? It's stable whether I push you in this direction or the x direction, right? The maximum is like super unstable. Whatever direction I push you, right, x direction or the y direction, you are moving away. How about the other third type of criticality? These are called saddles, right? They are called passes, mountain passes, right? They are somewhere in between, right? So you push along the x direction, right? You are stable, right? And you push along the other direction, the orthogonal direction, you are unstable, right? So these are somewhere in between. So you are now in looking at 2D functions, there are 3 types of critical points. Can you repeat that question? I'm not sure if I follow fully.
In Scalar, some direction if you push the ball, it will fall down.
Yeah,
Some places you push the ball, it will come back.
exactly.
But some places where you push the ball and it will fall still stable and won't come back.
Oh, okay. Okay, that's a good point. So what you're saying is if I push it a little bit, will it go to another point which is critical, right? Another point where the gradient is 0, right? That's a very interesting question. Again, that does not occur when you make this assumption about degeneracy, right? So imagine that you have like a true valley, right? Like a V-shaped valley, right? So you are at a slope and everything here in the valley are all at the same height. So what you're saying is true, right? I push along that direction, the gradient continues to be 0, right? So it turns out that if you assume that there is that the degeneracy condition is met, right, as in all the points are generic, then those kind of values also do not appear, right? Yeah, so that's a good observation though, yeah. Right? So it essentially means that all the critical points are isolated points. You don't have a line of minima, you only have a point minimum. Okay, good point. Okay, so now we know that there are 3 types of critical points, right? And the way to capture them from the Hessian is just by looking at the number of negative eigenvalues, right? So this is something that you can try and relate now, right? So this works even in higher dimensions when you are looking at 3D, right? Again, by looking at the number of negative eigenvalues of this Hessian matrix, you can capture how many, what type of criticality you are, right? So you already noted that. So we'll have other pictures. So we will see that connection, right? So the definition is still the same. There's no difference. I still call f as a Morse function if none of its critical points are degenerate. So I'll quickly look at one result in Morse theory, then we'll define the Reeb graph. So let's look at these critical points again and see how the function behaves in the neighborhood, right? So I'm showing you again the 3 types of critical points for 3 different functions, right? You may have seen these quadrics, right? X squared plus y squared and so on. So you can imagine how the gradient, so maybe as an exercise, right? We won't have time to do it now. So you can write down these 3 functions, compute their gradient, right? And compute the Hessian at that point. So assume that particular point is origin, right? So the blue minimum, the black maximum, the gray minimum, the blue maximum, and the gray and blue saddle. Assume that those locations are origin. Try to compute the gradient and the Hessian and see how many eigenvalues you get, negative eigenvalues you get for each case, right? You will see that for the minimum, the number of negative eigenvalues will be 0, right? And the next it will be 2, then it will be 1, right? This observation, okay, so remember what did we count when we talked about stability? We talked about how many directions can I push you for you to be unstable or stable, right? So if you are at a maximum, there are 2 directions in which you are unstable. So that's the number of negative eigenvalues. For a minimum, this is 0. For a saddle, this is 1. Okay, so you are counting how unstable you are. Okay, right. So you don't have to read the actual lemma. That's not important. This is for your later reference. But I'll go through this, right? So the Morse lemma is a kind of the fundamental lemmas in this study of Morse functions. Yeah, question.
Yeah, one question in general, d dimensions. So if Hessian has all the eigenvalues same sign, then it's a maximum and minimum. But if it's intermediate
No, so you just have to look at how many negative eigenvalues. Whether they are equal or not is irrelevant, right? Yeah. So remember, we assumed that the Hessian is non-singular, so positive or negative. We want to count the number of negative guys. Right? It doesn't matter, as we will see. It's actually more powerful than that. So you don't care about the actual values. You care only about whether they are negative or not. Yeah. Yeah.
Then we'll have a, so we have two directions like that.
Right. So if the eigenvalues are equal for that particular set of coordinates, right, where they are equal, all you are saying is that the partial derivatives in those directions, they are equally stable or equally unstable. That's all. So we don't actually care about that, is what I'm trying to say, right? So this will probably be clear from if I state this lemma, right? So the Morse lemma says that, right, no matter what function you choose, right, as long as it's a Morse function, doesn't matter what function, it could be fourth order, degree 10, whatever, right? Not even polynomial, right? Any function you choose, right? If it is a Morse function, right, then the function behaves in this following way within a neighborhood of the critical point. So we know that there are only 3 types of critical points for 2D functions, right? And what the Morse lemma says is that the function is either equal to x squared plus y squared, or x squared minus x squared plus y squared, or minus x squared minus y squared within a small neighborhood of this critical point, right? So it means that locally in the neighborhood of the critical point, your function can be approximated, right, to a quadratic function, right? And if you can choose a small enough neighborhood so that the function is exactly equal to a quadratic function, not even an approximation. That's what the lemma says. So it's a very, very powerful lemma, right? It's saying that any function behaves like a quadratic function near the critical points, right? And this is also linked to the classification result, right? So you are just counting how many unstable directions, right? That's also related to this. Okay. So if you have this picture in mind, that's sufficient. We don't have to go to the formal definition here, right? What is important for me is the Morse index, right, which is the number associated with each critical point. So we asked this question: how many critical points are there, and how many types of instabilities are there, right? This classification came from the Morse lemma. So for 1D functions, this is in the neighborhood of a critical point. The function behaves either as x squared or minus x squared, right? For 2D functions, the function behaves like we saw, either as one of these 3, right? 3D, it behaves one of these 4 ways, right? So I give now a number to each type of criticality. This number is just counting the number of negative eigenvalues, right? The number of instabilities. So minimum is always 0, right? Maximum is always equal to the dimension of the space, right? Or right? So it's 1, 2, or 3 depending on the number of variables you have, right? And you have other critical points. So in 3D, you actually have 4 types of critical points: minimum 0, maximum 3, and then 1 and 2 saddles. 1 saddle and 2 saddle. Okay. This is what we need out of Morse theory, right? So Morse theory, one of the primary results of Morse theory was the Morse lemma, right? And what we are trying to take away from Morse theory is this Morse index. Okay. So quick, again, pictorial introduction to manifolds. We don't necessarily look at functions defined on Euclidean space. We look at functions defined on so-called manifolds. Manifolds are Euclidean, but locally Euclidean, So one example is your circle, right? If you take any point on the circle and you take a small neighborhood, right? This neighborhood is like the Euclidean space, right? It's like the real line. As in, you can take you have a map from the small neighborhood of your point to the real line, right? This is what we call as a manifold. This holds even in higher dimensions. You take a sphere, you take any point, right? So if you are an ant living on that sphere, then what you see is flat land, right? So you see R2, right? Similarly, R3 and so on, right? So we work with such spaces, right, that are locally Euclidean. These are called manifolds. So manifolds can also be like this. This is a torus, right? Every point, you pick any point. Again, the neighborhood looks like R2, right? It's not a linear transform from your neighborhood to R2, but there is some kind of a deformation, right, to R2. Right? So we will now talk about functions that are defined on manifolds, right? Yes, question. Good question. So I guess the question is every space a manifold, right? No, not every space is a manifold. I'll give you a counter example. So think about your book and the spine of the book, right? You take the spine of a book. There are multiple pages. You pick a point on that spine, right? You take any small neighborhood, you will get these pages. That's not like R2 or R3 or anything, right? So there are some spaces like this which are not manifolds. Okay, so not every space is a manifold. Does that make sense? Okay. So we want to define functions on manifolds, right? So the question you may want to ask is, how do I define gradients, right? This is a tricky question. So there are formal ways to do this. We will assume some kind of global coordinates so that I can define gradients, right? But usually they are defined using something called local coordinates. We will assume that f, the function, is always again differentiable, right? We will always assume that that it is a Morse function, right? That none of the critical points are degenerate, even here. Right? So you don't care about this. So this is the formal way to say this, in case you have seen these terms, right? So the set of all Morse functions, right, is a subset of the set of all smooth functions, right? So if you know what this means, so the set of all Morse functions is dense in the set of all smooth functions, right? So more intuitively, what this means is you pick any function and you perturb it a little bit, right? You will find a Morse function in your neighborhood, right? That's what it means. Right? So we will always, like I said, assume global coordinates. So for example, in this case, if you have a function defined on this object which has 2 holes and so on, you will assume that the x, y, z coordinates are present. Okay? So let's talk about, I'll just give an introduction to level sets that will quickly introduce Reeb graphs pictorially, then maybe we will break, right? So remember this picture that we saw when I was talking about visualization. This is called a level set. There are many names. You can use it interchangeably, level set or isocontour or isosurface, right? So these are all pre-images of a given scalar value. So you pick a height, an elevation, all points that are at that elevation is called a level set. That makes sense? So F inverse of C, right? So this is also a level set, F inverse of some scalar value. All points which have a given scalar value. Right? So these are more practical examples. I will give simple illustrations so you will be able to understand it. Let's look at simple functions and understand level sets. So the domain is not going to be your R2, R3 anymore. They are all going to be manifolds, right? So here, this is a simple, very, very simple manifold. It's your sphere, right? And what is the scalar function? It is the height function, the height from the surface, right, from the floor. That is the function I'm going to look at, right? What are the level sets of this? So set of all points at a given elevation. So what will that be? These will be circles. So good. So you have an idea of what level sets are, right? But this is a very simple case. The level sets are all the same. They are all circles. So put your topology hat on now, right? So you can deform any circle to any other. They are all the equal for me, right? So there is nothing interesting happening here in terms of topology. All the level sets have the same topology, right? Okay. So let's, just to make sure we understand, let's pick another domain. Okay, same function, different domain. The domain is now a ball, 3D. What will be the level sets? Disks. Great. So again, nothing interesting happening in terms of topology. They all have the same topology. They all are disks. One can be deformed into the other. Now, the third example is the same domain, a ball, but now the function is 0 at the center of the ball, and it's increasing radially out. As you go radially out, the function increases, right? What will be the level sets? They will be concentric spheres, right? But again, nothing interesting happening in terms of topology. They all have the same topology, just the geometry is changing, right? So now let's move on to something else, a height function, but now defined on a torus, right? What will be the level sets? Right. So you expect something different, some ellipse or circles and so on, right? So let's look at them, if you can see the screen. So you have some ellipse, became a figure of 8, well, not really figure of 8, it became two disks that are touching at a point. And as you keep increasing the function value, you actually got two components of this level set, right? There were two disks which again merged into one and then vanished, right? So this has slightly interesting characteristics in terms of the topology or the connectivity of the level sets, right? So for now, all we care about is number of connected components. You know this from graphs, you know number of connected components and so on. So the question is, where did the topology change? As you change the function value, what were the locations at which the topology of your level set changed? These are exactly the 4 points, and they happen to be the critical points, gradient 0, right? Exactly those points are where the level set topology also changed, right? And how did it change? At the minimum, what happened? A level set, one component appeared from nowhere, right? So that's also change of topology. Empty set to one component. And maximum was where that component vanished. We call it death, so dies, right? Saddles were what happened? What happened at saddles? Either 1 became 2 or 2 became 1. So both can happen, right? So you see a connection. Morse theory is actually the study of this connection between level sets on this topology, connectivity, and critical points of functions, right? So this is exactly where the Reeb graph comes in, right? I want to capture the change in this level set topology, right? And I want to capture it by looking at the quotient space, right? So in simpler terms, what we are doing is you are taking every connected component and shrinking it to one point. Okay? You take every connected component of the level set, shrink it to a point. Right? Imagine what will happen to the collection of level sets. Right? So that exactly is your Reeb graph. So as you sweep up, one connected component shrinking to a point, and then this. Does that make sense? Right? So every connected component is shrinking to a point. This is also called the quotient space under an equivalence relation, right? So you know about equivalence classes and so on, right? So the equivalence relation here is that 2 points are related to each other if they belong to the same level set component, right? So under this equivalence relation, you have different equivalence classes, right? And you can talk about the quotient defined by this equivalence relation, and that's exactly the Reeb graph, right? So you give me a function f defined on a domain, the quotient space is the Reeb graph on the right. Okay? So this is how it is defined. Why is it called Reeb? Of course, the name is after the mathematician who defined it over 60 years ago now. Right? Fine. So with that definition, I think I will stop. We can study a little bit more about the properties of the Reeb graph after the break.